Well, but you get it. There's friction. And the idea being that if the bowling ball doesn't have much friction and you push it along, then it can go for a long time. And it has a bunch of kinetic energy in it as it goes along. If you send it with the same speed but put it in this box, give it some initial speed, then you'll see that, whoop, box falls over. It slows down a lot faster. So where does that energy go? Well, we think that it goes into that kinetic friction. The sliding motion on the carpet creates heat in the carpet. It also creates heat in the bottom of the box, warms it up, and therefore slows down that relative motion of the box and floor. So, and what does it do to? Well, microscopic bumps and holes crash into each other, causing friction force. So we're going to talk about this in terms of forces and dynamics today. Okay, so let's go through a couple of announcements before I get going on it. Nuit Blanche is coming this weekend, so maybe plan to check that out. It's all over Toronto, including there's events now in Etobicoke, North York, and Scarborough as well. And then there's this place. Yeah, so this is 255 McCall Street. It looks literally like this. It's all these tables, one table per student. You sit there for 80 minutes and write a test. So that's where you'll be. You'll be fine. It's just the same sort of physics stuff what we're doing. Just I want to see how you do when you're not connected to any electronic devices. So it's Tuesday, October the 11th. Students will begin writing at 6:10. We're going to try to admit everybody in the room at 6 o'clock to get your seat. Covers chapters 1 through 4, all this stuff we've been talking about, plus stuff we've been doing in the practicals. Next week, I've planned, instead of doing an experiment during practical, we're just going to do like a practice midterm, sort of very, very similar to what you're going to be seeing, but in fact, I think it's last year's midterm, but it's just like a group work activity where you're trying to, practice, go through it together. There'll be 10 multiple choice questions. You put your answer in a little bubble sheet. There'll be one written question. You'll have a separate sheet that you'll write the written answer question on, and then that gets scanned by April, and then someone actually marks it on their screen. You're allowed a calculator and an aid sheet that you must prepare yourself. So don't forget those two things. I'm hearing noises back here. You go away now. I guess you could have a very fancy graphing calculator. It's okay with me, but this is sort of the standard sort of $30 model that's at the U of T bookstore, which I like. Got sine and cos on it. You have a question back there? Can't hear you at all, I'm sorry. I have to get a lot closer. You have to just yell as loud as you can. I just literally cannot hear what you're saying at all, sorry. Yeah, you're allowed a graphing calculator if you want to, but you won't need it. You should just get a calculator that, that will do sine and cos and stuff on it. I mean, my idea is that I think the reason graphing calculators are sometimes forbidden is because you can store lots of equations in them, but you could also write those down in your aid sheet, right? So that's fine too. Yep. Yes, that's a great question. Aid sheet can be double-sided, so it's a letter-sized piece of paper written on both sides. And I will provide things like numerical constants and how many inches in a foot or these kinds of things, or 9.8. But what I will not provide for you is all the equations, like those equations of constant acceleration, or I don't know, any equations that you find useful in this course, you should write them down in your aid sheet. Like what I would do is when I'm doing my homework, I'd start making my aid sheet just with all the equations that I find useful. And then you have that with you, and you're kind of used to it, it's your own thing, rather than someone else's list of equations. And this is very important, and I'm sure you know this, but I'll just repeat it. You're not allowed to have a phone or a smartwatch on you during a term test at U of T. Can't do it. So or a laptop or anything like that can communicate with other people. That's the whole idea, is we're trying to isolate you from electronics for 80 minutes. You can put them in your bag somewhere where you're not allowed to look at them. So hence the reason why you really need a calculator. And sooner you get it, the better, so you can practice with it, so you're not just used to using your phone, as we all are for calculators. And then April's put this announcement that if you have a time conflict on Tuesday evenings, both the term tests this semester, October 11th and November 15th, are on Tuesday evenings. So there's a little form called Sign Up Sheet for Alternative Sitting. Just click on that. We'll try to find you an alternative time to write the test. But there's a deadline. I'd like you to fill this out by Monday at the latest so we can book a room for you. That's it. Yep. Yeah, I guess that's a good question. Yeah, is there going to be a clock that shows what time it is? So there are clocks in the examination center, sort of all over the walls, and hopefully those are correct. Also, I guess we'll announce when, if you're halfway through the test and there's 10 minutes left and stuff. But if you want to bring a non-smart watch with you, that's allowed as well, like to tell the time, like an old-fashioned kind of watch. And maybe you, sir? So if you have a time conflict at the time, you fill out that form, and April will let you know what's going on with the alternate sitting. I think it's before, in the hours before there. But we'll try to find a time when you can make it, when you don't have a conflict. I don't really want you to skip class so you can attend my midterm. It's not a good idea. All right, so let's get into a little bit about friction. We do have this idea that if I slide that box with the bowling ball along, it will slow it down. So sometimes friction slows things down, but not always. And one way it sometimes happens is when the surface is moving. If I have this truck and it's accelerating towards the right, and there's a box sitting on a flatbed on the back of the truck, well, it's going to speed up as well. And the reason it's speeding up, I think, is because there's friction from the truck onto the box, right? That's sort of pushing that box forward. So if the surface is moving, then you can certainly imagine friction speeding things up. Also, I've been going over this a lot, but if static friction of the floor on the bottom of your shoes is what allows you to walk. And walking can certainly involve speeding things up. And it would not be possible if the floor was frictionless or covered in marbles or something like that. Okay. Why does friction exist? We mentioned that no surface, certainly on a microscopic level, is going to be perfectly smooth. So whatever is on the top will have kind of stalactites or something, and what's on the bottom will have stalagmites, and they'll kind of lock into each other or hit each other. And so if you try a sideways motion, then there'll be some resistive force there to that motion. That's where friction's coming from. Because at the microscopic level, nothing is smooth. And, rather than get into all the experiments, so the equations for friction are all experimental results. And so your textbook really heavily goes into a bunch of videos on experiments, and we'll get into that today. But what I'd like to start with is just kinetic friction, because it's so simple, and we'll do a little example of it. It's sometimes called sliding friction. And I hope you can just sort of believe me, when two flat surfaces are in contact, there's going to be some kinetic friction. It'll slow things down. And there's a nice experimental result, which is, it looks terrible with all the subscripts, sorry about that. But basically what you're saying here is that the magnitude of the kinetic friction force equals, this is this HDMI splitter business again. Don't like you, splitter. Equals some dimensionless constant. Which is a Greek letter called mu, like what the cow says, mu. And then times the magnitude of the normal force of the surface on the object. So if the surfaces are pressing down on each other more, you get more kinetic friction, I guess. And the direction of the kinetic friction is always opposite that sliding motion. It wants to slow down the sliding motion. And in fact, it's also creating that heat, and that's where that's coming from. So why don't we do first learning catalytics? Get you guys doing something. So this is a bit wordy, but a wooden block has a mass of 10.2 kilograms, meaning that the force of gravity of Earth on the box is 100 newtons. And since the box is not accelerating up or down, that means that the normal force of the surface upwards on the block is also 100 newtons, right? So N equals 100 newtons. Normal force of surface on the block. Anyway, there's a 5 Newton horizontal force applied to the block, pushing it to the right. And at this instant of time, the block is sliding to the right at 5 meters per second. What is the force of kinetic friction of the surface on the block? And maybe you don't need to use all those numbers. Some of them might be red herrings. But think about it, and then pair up and share. Give you a minute to think about that. Pick best answer. You guys got an answer? Seeing 420 responses. Let me give you another 10 seconds. Try to click something in, and then I'll discuss. Remember the equation. I'll write it without so many subscripts. F is equal to mu times n. And that's kinetic. I can put a little sub k for kinetic. That's what we're trying to do here. Okay. Going once, going twice, and stop delivery. So 10 newtons to the left. So it's 100 times the 0.1, I think is where that's coming from. So well done. I'll sort of go through that a bit. Good job. So if I wanted to do the force diagram of the block, there'd be the normal force of the surface on the block. That's equals the 100, because the force of gravity of the Earth on the block is mg, and that's 100. And then there's this forward force, the force of like the hand or something like that on the block is the 5 newtons. And then this backwards force, F sub k. And there's the equation. F sub k is 0.1 times 100. You get 10 newtons. And you just have to know, since it's sliding to the right, okay, V is to the right. And therefore, Fk vector is to the left. Okay, so it's going to be 10 newtons. You can get the 10 newtons part. The magnitude comes from this equation, and the direction comes from the velocity. So maybe we should go just a little farther with this. I wish I could just keep that let me just quickly draw it again. It goes like this, right? There's normal, there's mg, there's this force of 5 newtons, and then there's the friction force. So the question is the block accelerating? Well, a sub y, if we set y to be up and x to be to the right, is equal to 0. It's going to be, 100 minus 100 divided by 10.2. Anyway, it's 0. A sub x is the sum of all the forces in the x direction divided by the mass, and this will be 5 minus 10 divided by 10.2. And so I actually got negative 0.49 meters per second squared. So what that means, since v sub x is greater than 0, it's plus 5 meters per second, the block is slowing down. Whenever you have the acceleration opposite the direction of the velocity, it means it's slowing down. If acceleration was in the same direction as the velocity, it would be speeding up. Okay? So this stuff comes up in 2 dimensions a lot. So there's often this sled that gets pulled. So let's do an example of one that's in 2D. So a slippery box of mass 5.0 kilograms, not frictionless, but there it is. We'll put it here at B, is pulled at a constant velocity by a rope which makes an angle of 20.0 degrees above the horizontal. So I can try to sketch that. Here's the rope. Maybe we'll call it R for rope. And there's an angle here, theta, is equal to 20 degrees, sort of up, 0.0. Okay, and then on the bottom here, the coefficient of kinetic friction between the box and the surface, mu sub k, is equal to 0.03. Okay. And I feel like I maybe tapped it. I'm glad you're here, Pius. You give me that feeling of, wow, you can see it, but I can't. It's not showing up on my screen now. It's weird, I can write. Off and on? Sure. It's weird because I know it's working, but I can't see anything. Maybe I'll just unplug it, plug it back in. Okay. We're good. So the system is the box, and V is constant. That's going to be important so that all the acceleration components are going to be 0. Doing well here. This implies that A in all the directions is equal to 0. So that means that the sum of all the forces in the x and the y direction are all going to be 0. And we're trying to find here what is the magnitude of the tension force, T, of the rope on the box. Okay, so in my simplifying diagram step, that's where I draw the force diagram. So let's try to draw all the forces. There's going to be the normal force acting up. There's going to be mg acting down. And there's going to be tension. That's going to be the diagonal force. And there's going to be the kinetic friction, which is I guess if the thing's sliding to the right, then it'll be backwards towards the left. Hope that's right. And I'm going to, again, set define. So I've defined the system as the box, and now I'm defining... It's just the day of technical difficulties. Define y to be up and x to be towards the right. So there's only one diagonal force, so I can draw a little right angle triangle and say that it's got a y component and it's got an x component, and I can find the components pretty easily from theta. This is theta right here, the 20 degrees. It's t sine theta is the y component, and t cos theta is the x component. So when I go to represent mathematically, what I like to do is just write out what the forces, the net forces are. F sub x, all the sum of all the f sub x's, which, don't forget, equals 0 because it's in equilibrium, it's got constant velocity, is going to be, I'm going to take all the forces to the right, add them, and then all the forces to the left and subtract them. So I get, there's a plus t cos theta, and there's a minus the friction force. So remember, friction is equal to mu sub k times n. So it's minus mu sub k times n. I'm going to call that maybe equation 1 because we're going to use that. And the sum of all the forces in the y direction, which also equals 0, so all the upward forces will be added, downward forces minused. So normal force is up, so n. The tension is up, so that's t sine theta. It's got an upward component. And the gravity is down, mg. Maybe call it mass box. Okay, we can call that equation 2. And what I'm going to do here is I'm going to solve for n in equation 2 and plug into equation 1 and solve for t. Because there's two equations, two unknowns here. Tension is unknown and normal force is unknown. I don't care about the normal force, so and I want to find the tension force, that's what I'm trying to find. So my strategy is to use one of the equations to solve for the thing I don't care about, and then plug it into the other equation, and then I should be able to solve out with no n's left. Okay, so equation 2 tells me that n is equal to the mass of the box times gravity minus t sine theta. So that's sort of interesting. The normal force is definitely not mg here. It's mg minus this tension, because it's being partly supported by the tension. And now I can take that and plug it into this equation up. That was from equation 2, so use equation 1 and plug it in there. That's always my trick. So from equation 1, I get that 0 is equal to t cos theta minus mu sub k times all this stuff. B, G, the normal force, minus t sine theta. And at this point, it's basically algebra. I'm going to gather terms of t on the left-hand side and solve it out. On the left-hand side. So we've sort of done the physics stuff, and now we're doing the algebra stuff. Mu sub k times t sine, that's a negative sign there, I think, minus t cos theta. I'm going to keep track of my minus signs. I think that all these are minus. Mu sub k, m sub b, g. So I can divide both sides by -1, I guess, and get a t, they're all positive, cos theta plus mu sub k sine theta equals mu sub k times the mass of the block times g. So t is equal to mu sub k times m of the block times g. So that's done. And we just have to plug in the numbers, I guess. Plus mu sub k times sine theta. So it's t is equal to 0.030, that was mu sub k, times 5, that's the mass of the block, times 9.8, divided by the cosine of 20 degrees. Make sure your calculator is set on degrees mode, plus 0.030 times sine of 20 degrees. And I got the tension is equal to 1.5174. Units should be newtons. Maybe rounded off to 2 significant digits, 1.5 newtons. This is a small force because it's a small force. Since mu sub k is low. It's 0.03, so. Okay, so it's an example. Okay, well, let us at least go through static friction. And I'll start you off with a learning catalytic question. So, basic idea of this frog sitting on a slope is that he's going to start sliding down the slope unless there's some force parallel to the surface holding him on the slope. So that's static friction. The object and the surface have kind of locked together. So once again, I think of those stalactites and stalagmites kind of going together on the surfaces. And now if you tilt them, they produce what is essentially a normal force, I guess, but it's a surface force that prevents slipping. It's again one of these as needed forces. There's no general equation for it. The direction is just whatever is required to prevent it from slipping. So if I look at that frog and I say, what's the direction of static friction on it? What I do in my head is I think, well, if there was no friction, which way would the frog tend to slip? And I think, oh, he goes down the hill. Therefore, the static friction must act up the hill to keep him from slipping. That's how I always try to figure that out. Okay, let's deliver the green car question. A car is parked on a flat horizontal pavement. Of these three forces, which of them should you add to the force diagram to the car? D, all of the above, or E, the gravity normal but not C? Give you a minute to think about that. Okay. If only we could get all our HDMI wires sorted out, that would work. You guys want to see what the survey says here? Going once, going twice. Let's see what people are saying. Laptop 2. 71% of you voted for not putting the static friction. So my thing with it is that the reason for a force diagram is to put forces on that have some direction, right? And so if a force is 0 in this special case, then you just don't add it to the force diagram. So that's, hopefully you agree with me about that. All you do is you just draw the normal force acting up of the surface on the car. That's a vector, and you're going to draw the force of gravity, Earth, on the car acting up. But there's no F sub S is as needed, and it's not needed if it's on a horizontal surface. Only if the car is parked on a slope. Or another thing that could happen is that someone could come along and push the car, and then there would be some static friction needed to keep it from going away. So, as needed. All right, should we try to go through some of these videos? There's a couple of videos I just sort of wanted to show you, experiments. They don't have any sound in them. Measuring the force needed to move a block. So it's just a little bit about static friction. She pulls this thing. It gets up to, that's a Newton meter, gets up to about 2 newtons. The interesting thing here being that she can pull 1 newton or 2 newtons, it doesn't matter. It's just, there must be a reaction friction force which is keeping it still no matter what she pulls. Until she gets to some sort of maximum value, I guess 3.2 newtons. After that, then it really does start to move. So the conclusions here are that if it's just at rest on a horizontal desk, there's only 2 forces, no static friction needed, so it's not there. Next experiment is that if she pulls with some force, then there must be some, because the block is not accelerating, the sum of the forces must be 0. We therefore conclude that the surface is exerting some horizontal component of the force. The book sort of talks about a diagonal force, and that this diagonal force gets sort of more diagonal. It's a combination of the normal and the static friction, but if she pulls with a stronger force, the static friction self-increases until it gets to some maximum, I guess, and then it starts to slip. So the pattern is that in each of the experiments, the surface exerts a force on the block that can be resolved into 2 vector components. The perpendicular component of the force is what we call the normal force, doesn't change. But the parallel component, the static friction, just changes as you apply a horizontal force to it. So this is another way of looking at it. If you're pushing this down on the block, the surface pushes on the object with a diagonal force, which you can split into components for convenience, called the normal force and static friction. Okay. So let's do another learning catalytics. See what you guys think about this. And we'll do 2 questions on this exact same situation. It's a wooden block with a mass of 10.2 kilograms. Again, the force, we've already done one. Actually, we'll do 3. The Earth exerts a force of 100 newtons. In this case, you're given that the coefficient of static friction between the wood and the concrete is 0.2. Remember, that's dimensionless, no units. A 5 Newton horizontal force is applied to the block, pushing it towards the right, but the block does not move. What is the force of static friction of the surface on the block? Give you a minute to think about that. Click in. My foot. If I rub my foot on the floor, I'm heating up the floor. See it? Sorry about that. My mic was off, but there's a thermal camera which shows infrared emission. And you can see that, like there's my hand. Okay. Emitting in the infrared. The floor emits an infrared because it's heated up when there's some kinetic friction of my foot sliding on it. So, awesome. Thank you, Pius. Did work. All right. Going once, going twice. Let's see what survey says. 66% are voting for 5. The next most popular answer was 20 newtons to the left. Okay, which I totally understand. Probably what you did was multiply the 0.2 times the 100 newtons, right? And you get 20. So which makes sense, but so what you did there is you actually, people who answered B, is you computed the Fs max, which is not the same as Fx. It's just like the possible that it can get to. So remember, well, we'll get to that in a bit, but the idea here is that it's a self-adjusting force. Static friction wouldn't have to be there at all unless someone was pushing it. The only reason it's there is because the person's pushing it. So actually, it's good to check. You computed that 20 newtons. That's good because 5 is less than 20, so that's important, actually. But it's not the answer to this question that I asked, which is what is currently, I guess, the static friction force. So that was a tricky one. And there's one more learning catalytics, but I wanted to show you some videos first about more expense. So the idea of these videos is that friction really is an experimental result. It's not a very fundamental concept like Newton's laws or something. So this is an experiment in which she slides it on different surfaces, a mirror, some rubber, so a wooden block, but on different surfaces below. And this is a measurement, it's a photograph. Whoop. You stop now, you. This is a photograph showing the force when it just starts to slip on the different surfaces, and it's different, 1, 2, 4 for the table, mirror, or rubber. So the surface affects it. What about the surface area? So what she does is takes it, slides it on sort of its medium side, or its biggest side, its medium side, and its smallest side. So the same exact block, but a different amount of surface area touching the surface. And what's interesting here is that it doesn't seem to affect it much. They all come out to be about 4 newtons, sort of within experimental uncertainties. And then what about if you pile more masses on the block? So 1 mass, she pulls it, takes a photograph of when it just starts to go, 2 masses, 3 masses. So in all these cases, we're measuring the maximum static friction force. And in this case, it increases, 1, 2, and 3. So with the different amounts of mass. So the experimental results here are 1, different surfaces definitely produce a different maximum static friction force. Experimental result number 2, different amounts of surface area between the object and the floor do not appear to change maximum static friction force. It's around 4 in each case. And experimental result number 3 is that the more mass seem to produce a more maximum static friction force. and then she asked the following question, which is, wait, is it the mass or is it the normal force? And so there's another experiment here, which is very cute, in which they take a tiny little skateboard and then measure the maximum static friction as 1.2 newtons, but then they push on the skateboard. What that does is, and it can roll, is that it only increases the normal force of the surface on the wood without increasing the mass of the wood, sort of like trying to separate out that variable. And the more you push down on that little skateboard, the higher force it requires to get the thing rolling. So experimental result number 4 is that the same wooden block with the same mass, when pressed down by a tiny skateboard, produced more maximum static friction force the more the skateboard was pressed down. So that indicates that it's not the mass of the object that matters, it's the normal force. So this is just to remind you, I guess, that these are all experimental results. And I have one more learning catalytics, which if you computed that 20, you're going to be happy. It's coming up. So this is a little awkward here, but there's so many subscripts, it's just ridiculous. But bear with me. The Fs max is equal to mu sub s, that dimensionless constant, times the normal force. So once again, mu sub s is a dimensionless constant. You just look these up in a table. Coefficient of static friction. And n is the normal force. So that's it. If you do the learning catalytics, we'll deliver this last one. So it's the same, this is the third time. But now we've got what is the maximum horizontal force that you can exert on the block and still have the block remain stationary? This is a question that comes up a lot as they say, what's the maximum force? Or sometimes if something's turning, you say, what's the maximum speed it can turn before it slides off? And in all of these cases, you're finding the limit, which is by setting Fs equals Fs max. So I'll give you a minute to think about that. You might notice that Fs max and Fk have the exact same equation. It's mu times n, right? But first of all, it's a totally different thing. So Fk is always the kinetic friction of a sliding object, whereas Fs max is this limit to something, the static friction. And then the other difference is that the mu is different. I'll show you in the next slide, but you can find tables of mu sub k versus mu sub s, and it's always a little larger. I think because when things are sliding, the surfaces are up high or something. When they lock together, though, then the maximum static friction is more. So mu sub s tends to be more than mu sub k. This is a really great question. Is this the same equation? No, it's different, but really similar looking. It is F sub s comma max is equal to mu sub s times. It's the subtle differences. F sub k is equal to mu sub k times n. Sometimes people just write it as F sub s is less than or equal to mu sub s times n. Is an inequality. F sub s less than equal to mu sub s. Okay, want to do the laptop 2 and see what people are saying. Now you got it. 20 newtons. That's where I'm getting at. Okay, if you push it with 25 newtons, then all of a sudden the static friction force will go away and it'll convert to kinetic friction. Oh my God, it's Friday. I'm losing you people. This is what I was saying, is that if you have rubber on concrete, the coefficient of static friction, mu sub s, is 1. Whereas the coefficient of kinetic friction is 0.6. Steel on steel, coefficient of static friction is 0.74 to 0.78. These are measured numbers. Whereas the coefficient of kinetic friction is again less. So what I want you to notice from this is that mu sub s tends to be greater than mu sub k. I think in all these cases, we're close. Oh boy. Next time I'm gonna have to give you like a really hard learning catalytics question right at 11:56. Or I lose you. But that's okay, it's Friday anyways. I hope you have a great weekend. On Monday, we're going to continue on with Chapter 4, solving dynamics problems in 2D. We're going to do some projectile motion. We'll probably do the monkey and the hunter experiment in Con Hall on Monday morning. So do not miss it. See you Monday.